So we just learned about the binomial distribution. We've also learned about the Bernoulli. Now we're going to learn about two more discrete distributions, geometric and negative, and then the next section is the Poisson distribution. So in all total, we'll have 4 discrete distributions we'll learn about. I'll probably only put, well, maybe not.
Did you have another copy of this one?
I don't.
Okay.
Sorry. Okay, for the geometric and negative binomial distributions, some textbooks have slightly different definitions than we do, so their formulas are slightly different. The concept is the same, but like we're going to define the geometric as the number of successes or number of trials up to and including your first success. Other textbooks don't include the first success. They just do the number of failures. Okay, things like that. So they might change it slightly, so just be aware of that if you ever switch from textbook to textbook. But if you know how to do this, you should be able to solve any problem that we give you. So we use the geometric distribution when we have a sequence of independent trials. Each trial has either success or failure. There's a constant probability of success, P, and we're interested in how many trials we need to get our first success. Why is this different than the binomial?
Binomial, are we counting the successes over a period of set trials?
Yep, so in the binomial, we count the number of successes over a set number of trials. So you know in advance we're going to do it n times, and we count our successes. Here, everything else is exactly the same, but we don't know in advance how many trials because we stop when we get our first success, and we just count the number of trials. So if we count our number of trials up to and including our first success, notice now our possible x values are 1, 2, 3, dot, dot, dot. In the binomial, you could have 0 successes, but here you keep going until you get your first success, which means you have to do it at least once. Okay? And it could potentially go up to infinity. The probability mass function is defined as 1 minus p to the power of x minus 1 times p. So what this means is if I'm only going up till I get my first success, then I need 1 success, and I actually need to fail x minus 1 times, because it was all the failures up to my first success. So 1 minus p is the probability of failing, and you need x minus 1 failures, and then you need just 1 success. Now this formula is actually really nice because you can get a nice formula for the cumulative distribution function. So the cumulative distribution is the probability that x is less than or equal to x can be found by 1 minus p to the power of x. None of the rest of them have a nice formula for the CDF, but this one does. The expected value and variance are, so the expected value is 1 over p, the variance is 1 minus p squared over p. So let's suppose you decide to roll a fair dice until you roll a 1. Let x be the number of times you have to roll the dice. So first of all, what is the PMF? What's the only thing I need to know to actually write my PMF? Just the probability. So what is P? 1/6, since it's a fair dice. So the PMF is going to be the probability that x equals a specific value is going to be 1 minus 1/6 to the power of x minus 1 times 1/6. So that's going to be my PMF. My CDF, the probability that x is less than or equal to x, is going to be defined as, let's see, 1 minus 1 minus 1/6 to the power of x. So next, find the probability that we will roll the dice exactly 5 times. Okay, would you rather use the PMF or CDF? Okay, if I want just one value, it's going to be easier to use the PMF since that gives us probabilities for single values. So it's going to be 5/6, 1 minus 1/6 is 5/6 to the power of x minus 1. So the power of 4 times 1/6. Basically, you have to fail 4 times, succeed 1 time. So my probability is 0.0803. Find the probability that we roll the dice between 3 and 7 times. Include the 7 and 3. So I need the values x equals 3, 4, 5, 6, and 7. I could find each of those values one by using the TMF, or I can try and use the CDF. Okay? So for example, if I found the probability that x is less than or equal to 7, let's see. So that could give me my upper bound. I'm probably going to want to subtract these two probabilities. What other probability do you think I need to subtract? I've heard one person say it, but you have to say it louder. Okay. It's going to be 2. Why is it 2? Because I want to include 3. If I subtract out x less than or equal to 3, then I'd be subtracting out the probability of the 3. So you're going to have to think about it each time. It's not, probably won't come very naturally for a while. You're going to have to think, well, what do I need to subtract to make sure I still include my 3? So this makes it easy. Now I can just use my CDF and plug it straight into my CDF. So it's going to be 1 minus 5/6 to the power of x is 7, minus 1 minus 5/6 to the power of 2. If I typed it in correctly, 0.415. Anyone else? Easier than trying to find the probability for 3 to 7, 1 by 1. And we like all these specific discrete distributions because they all have nice formulas for the expected value and variance. So my expected value is 1 over p. So 1 over 1/6 gives me 6. So on average, I will have to roll the dice 6 times before I get a 1. And for my variance, this is going to be 1 minus 1/6 squared over 1/6. .83. So my standard deviation is the square root of that, so 2.4. So if you think about that, again, we don't have a really direct way to apply our standard deviation, but we know that on average we'll have to roll the dice 6 times, but my standard deviation is 2.4, which means that I'm going to expect quite a bit of variance. Like I'm really not going to be surprised if I only roll it 3 times or if I roll it 9 times before I get the 1. My variance seems pretty big. Okay. So that is a geometric distribution. Sorry to finish. Any questions? So in this next example, we decide to flip a fair coin until we get a head. Let x be the number of times you have to flip the coin. Okay. So I thought it might be nice to have your probability distribution so you can look at it as a graph. So the probability that I have to flip it once is 1/2. That makes sense, right? The probability that I have to flip it 2 times is 1/4, 3 times is 1/8, 4 times is 1/16, etc. Okay, also, just so you can look at it and see, here's the CDF. because it's the probability that x is less than or equal to x, is 1/2, 3/4, 7/8, 5/16, 31/32, 32, etc. So we decide to flip a fair coin until we get ahead. So that's what makes it geometric. I stop on my first success. What is the probability of getting ahead? 1/2. So when I ask you what is the PMF, so the probability that x equals a specific value, well, I think, okay, I need to have so many failures. How many failures do I need? I need x minus 1, and then I need to get my first success. I can simplify this to 1/2 to the power of x minus 1 times 1/2. And just on this one problem, how can I simplify that even further? 1/2 to the power of x. Okay. It doesn't usually simplify that nicely. And what is the CDF? So for that we need the formula. That's a formula that I don't have memorized. So 1 minus x to the x, or 1 minus p to the x. So you guys can flip up easier than I can, is that right? Okay, so 1 minus 1/2 to the x, so that's going to be 1 minus 1/2 to the power of x. So let's try it. So let's find the probability that x is less than or equal to 3. Okay, would you want to use the PMF or CDF? Okay, so we can use the PMF. So if I use the PMF, that means I need to find the probability. Which values do I start at? Do I need a 0 in there? So I need the 1, the 2, and the 3 if you want to use the PMF. Okay. Remember, 0 is not in there because you have to toss at least once to get your first success. And I need to plug each of these into my formula. So 1/2 to the power of 1, 1/2 to the power of 2, 1/2 to the power of 3, so that gives me 0.875. Was there an easier way to do this? If I use the CDF instead, so the probability that x is less than or equal to 3, I can use the CDF and just plug it into the CDF. Which still gives me 0.875. Okay, notice here though, if you're on the test and you can't remember which one to use, you can use both. Either way, you'll get the same answer. Find the probability that we have to flip it more than 7 times. So we're looking for the probability that x is greater than 7. Now this way, there is only one way you can do it. Okay? Because if I wanted to find each of the individual probabilities, I'd have to find it for 8, 9, 10, 11, 12, 13, 14, all the way up to infinity, and technically it would never stop. So what is an easier way to do this? Probability that x is greater than 7 is the same thing as 1 minus the probability that x is less than or equal to 7. So it's going to be 1 minus, and I'm going to use my CDF here. My CDF is 1 minus 1/2 to the power of x, so 7. .0078125. Which makes sense, right? If you're flipping a fair coin, you would probably expect that you don't have to flip it more than 7 times to get ahead. That'd be pretty surprising if we had to flip it more than 7 times to get my first head. Questions on it? Feel okay with it? Okay. Find f of 3, capital F of 3. Mostly I just put this on here to remind you of our notation. What does that mean? It means find the probability that x is less than or equal to 3. So to do that, we just plug it into our CDF, or we've actually found it up above. We know that it is 0.875. The expected value. Okay, what was our formula for expected value? Look up on the previous page. It is 1 over p. So 1 over 1/2 is 2. So on average, you'll have to flip your coin 2 times before you get ahead. Sounds reasonable. And the variance is going to be a 1 minus p squared over p, if you look up at your previous page. Okay, so 1 minus 1/2 squared over 1/2. So it gives me 3/2. So my variance is 1.5. So let's see. Thumbs up if you like the geometric. Thumbs down. Okay with it. How you feel? Confident you feel?
With the expected value, does that include the success then? So the second one, it would be a success?
Yes. Yep. X includes our first success, so the expected value of x will still include our first success. So the next distribution is actually very similar to it. I'm not actually sure why it's called the negative binomial distribution. I've never tried to figure it out. But we use the negative binomial distribution when we have a sequence of independent trials. Each trial has either success or failure. We have a constant probability of success. And we're interested in how many trials we need to get our success. So the only difference between this and the geometric is on the geometric we stop when we get 1 success. But it might be even more interesting to us to stop when we get 3 successes or stop when we get 10 successes. So we count the number of trials we need to get our success, or our 10th success, or our 7th success. Okay. Now, if you need to get 10 successes, how many times do you have to flip that coin? At least 10. Okay. So your possible xi's are going to be r plus 1, r plus 2. You have to do your experiment at least r times if you want r successes. Okay. The probability mass function looks a little more complicated, but still nothing that we can't plug our numbers into. So you need to have x minus 1 choose r minus 1. Notice we want r successes, so we have p to the r. And then that means we need x minus r failures, so 1 minus p to the power of x minus r. We have a formula for expected value. Notice all that happens is the r appears, and for the variance, again, actually variance changes a little bit from the geometric. So an example of this is we decide to toss a fair coin until we get the second head. Okay. So this is my probability mass function. Notice the probability that I only have to toss it once is 0. You have to toss it at least 2 times. It's the same probability for 2 and 3, and then it gets steadily smaller. And they also gave us the CDF, probability that x is less than or equal to x, just so you can kind of look at those numbers. Really, by the time you get to 14 tosses, it's almost certain that you've gotten 2 heads by now. So again, we decide to toss a fair coin until we get the second head. So we have r equals 2, and then we still need to know the probability of getting a head. The probability of getting a head is 0.5. So notice for the negative binomial, I have two parameters that I have to keep track of. So let's find the probability that we have to toss the coin 6 times. So we're looking for the probability that x equals 6. So you might need to flip back and forth so you can look at the formula. The first part is the hardest part for me to remember. It is my x minus 1, choose r minus 1. Is that correct? Okay. So x, how many times, or x is 6, and so we have 6 minus 1, and r is the number of heads I want. I want 2 heads, so 2 minus 1. And then the next part is I say, okay, well, how many successes do I want? I want 2 successes, or the probability of getting a head is 0.5, and I need to get that twice. And then the probability of getting something that's not a head is 1 minus 0.5, so 0.5, and I need that 4 times. So just like the binomial, they need to add up to 6. So we have 5 choose 1 times 0.5 to the 2, 0.5 to the 4. So 0.0781. Find the expected number of times we have to toss the coin. So you look back at the formula, it's r over p. So 2 over 0.5 gives me 4. That kind of makes sense, right? If I expect I have to flip it twice to get 1 head, then I might expect that I'd have to toss it 4 times to get 2 heads. So next step, find the standard deviation of the number of times we have to toss the coin. We don't have a formula for standard deviation, but we do have a formula for variance. So it's going to be the square root of r times 1 minus p over p squared. R is 2, p is 0.5. So 2, anyone else? So for my next example, Bob is a high school basketball player. He's a 70% free throw shooter. That means his probability of making a free throw is 0.7. We are interested in how many shots it takes him to make 3 free throws. So what is the probability that it takes him 5 shots? So first of all, do you recognize that this is negative binomial? So we're interested in how many shots up to the 3rd free throws. So we have the probability of making a free throw is 0.7, and we need him to make 3 free throws. So what is the probability that it takes him 5 shots? So we're looking for the probability that x equals 5. So when we start our formula, it's x minus 1, so 5 minus 1 over r minus 1. And then at this point, I usually try and do it by logic. So I say, okay, the probability of him making it is 0.7. I need him to make 3. Then what's the probability of him missing? It'd be 1 minus 0.7, and how many do I need him to miss? I need him to miss 2. So about an 18% chance probability that it's going to take him 5 shots to make 3 free throws. What is the probability that it takes him more than 5 shots? How are you going to solve this?
I have a question for one.
So does this make sure that the fifth shot he makes it, does that include that?
Yes. So this means on the fifth shot, he makes his third free throw. So we include our success. So for this probability that x is greater than 5, that would mean I'd have to include 6, 7, 8, 9, all the way up to infinity. So we don't want to do it that way, so let's use the complement rule. So this is 1 minus the probability that x is less than or equal to 5. Now this means I am going to have to find the probability that x equals 1. Actually, do I have to start at 1? No. What's my smallest value of the number of shots he can make? 3. Good, that'll save some time. So 3, 4, or 5. Because he has to make try at least 3 times to make 3 shots. So probability that x equals 3, that would be 3 minus 1 over choose 3 minus 1. He needs to make 3 shots, miss 0 shots. For the 4, it's going to be 4 minus 1, choose 3 minus 1. He needs to make 3 and miss 1. And then we already know the probability that x equals 5. So 0.16308. So about a 16% chance that it's going to take him more than 5 shots. So what is the expected number of times he has to shoot before making 3 free throws? So I need to find my expected value, which is defined as R over P. So R is the number of shots we want him to make. P is the probability of him making it. That's not right, is it?
R is 3.
Oh, that would make a difference, wouldn't it? So 4.2. Okay, so on average, he'll have to shoot 4.2 times. Of course, he can't shoot 4.2 times. That is an average over the long run. And finally, if I want to find the standard deviation, first I have to find the variance. So R times 1 minus P over P squared. So 3 times 1 minus 0.7 over 0.7 squared. $1.836. And that finishes our negative binomial. Questions on the negative binomial?
Okay, how's the logic for the negative binomial different from what we just did before?
The geometric?
Yeah.
So the difference between the negative binomial and the geometric is the geometric just counts up to your first success, and the negative binomial counts your rth success. You'll notice, though, that the formulas are very similar for the PMF. So for your geometric, if you only want one success, there's only one way to get one. Well, you don't have to worry about counting the ways to get one success because you're only doing your first success, and it has to be your last time. And so all you have to worry about is you say, okay, well, I want to get one success with a P, and everything else has to be a failure. Okay? But if you want, so this is if you only want your first success. If you want your rth success, then you use the negative binomial. And again, I don't know why it's named that and not like geometric extended or something like that. But you say, okay, well, I need to have r successes and x minus r failures. But when you think about it, there's a lot of ways that I could get my r successes. So if I want 3 successes, I could have the first one be good, the next 2 bad, the next one good, the next 2 bad. Or I could have good, good, bad, 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 good, something like that. So you have to try and figure out all the different ways you can get your r successes, which is why we have to throw in this combination. Okay. The reason that we have our minus 1s is that we know our last trial has to be a success. So we're really only taking the x minus 1 old trials and trying to choose our minus 1 successes. So that's where we get the formulas. They're very similar, and that's why they go in this situation together, but I don't know why the negative binomial is called binomial. It makes you think that's more binomial, but it's really more geometric. Our next distribution is called a Poisson distribution. Okay. And I made the decision, since we have 7 minutes, I'm going to show you this one, but we will skip this for the homework and the exam. So it's a fairly common one, so you'll have seen it once, but I will not make you do this for the homework or exam, just to save us a little time. Okay. This does mean that sections 3.1 and 3.2 will be due tomorrow. Okay, so that's binomial, geometric, negative binomial. So the Poisson distribution is different than what we've done so far. Okay. So in the previous times it's been like trials, so like I do something over and over and over again. Now what happens is we use the Poisson distribution when we want to count the number of occurrences of an event per unit of like time, distance, volume. So we say like how many times does a bird hit the window in a day? Okay. Notice it's not like we're throwing the bird at it 100 times and seeing how many times he hits it. It's more of just the we just count how many times he does it in this unit of time. Okay. Or if you have a building with, and you know the square feet, how many times does the bird hit that amount of square feet? Okay. Things like that. So it's a unit of time, distance, volume, etc. So, and then you have the probability of the event occurring is the same for each unit of time, distance, or volume. So the number of times the bird hits the window should be the same each day, or each hour, etc., on average. Okay. So we let x be the number of occurrences in our given interval. Possible x values are 0, 1, 2, 3, potentially up to infinity. The probability mass function is given as this. Okay? So we have e to the negative lambda, lambda to the power of x over x factorial, where lambda is the average number of occurrences in our given interval. You can say that x is distributed p of lambda. The book uses this notation. I've really never seen anyone else use it. I would prefer to write out Poisson lambda, because this makes me think that it's just a probability. The expected value and variance are coincidentally both equal to lambda. So examples of the Poisson distribution is like the number of customers who arrive at the counter in 1 hour, or the number of major fires in a city during the last 2 months, number of typing errors per page in a book, number of dirt specks found in 1 square of plastic wrap. Things like that. So we have a specified unit of time, length, volume, anything like that, and we're looking for the number of occurrences. So this is how it plays out. So we measure software quality by numbering the number of errors per 1,000 lines of computer code. Suppose the number of errors per 1,000 lines of computer code is described by a Poisson distribution with a mean of 4 errors per 1,000 lines of code. Okay. So I expect 4 errors per 1,000 lines. So now I might ask you something like, find the probability of obtaining 8 errors in 2,500 lines of computer code. The first thing you need to do is a lambda. Okay, what do you think your lambda is going to be?
What you're expecting?
Okay, what I expect. So how many would you expect in 2,500 lines of code?
10.
Okay, why?
Well, I think it's 4. Expect 4 per 1,000 lines, or times that by 2.5, and so it's 250. Or
Yes.
10. Yeah.
Okay, so if you expect 4 in 1,000 lines of code, then in 2,500 lines of code, you'd expect 4 times 2.5, which is 10. So that's the hardest thing about the Poisson, is each time, for almost every problem, you have to find a new lambda, because they might change the number of lines of code you have. Okay, so now find the probability of obtaining our 8 errors. So I'm looking for the probability that x equals 8. So our formula is e to the negative lambda, lambda to the power of x over x factorial. Correct me if I'm wrong, that's just pulling out of my memory. So it's going to be e to the negative lambda. Lambda is 10. E to the negative 10 times 10 to the power of 8 over 8 factorial. .1125. Anyone else? And then we start changing things. So for my next thing, I ask you, well, what's the probability of obtaining 7 errors in 10,000 lines of code? So in this situation, notice my lambda is going to change. What would lambda be this time? Okay, 40. So the probability that x equals 7 is going to be e to the negative 40 times 40 raised to the power of 7 all over 7 factorial, which you could put in your calculator and figure it out. But let's just skip on to like number 3. So what is the mean number of errors in 7,000 lines of code? So we know that the expected number is 4 for 1,000 lines. So if I want 7,000 lines, I need to times it by 7, so it would be 28. Then if you want the expected value, or your mean number, the formula is just equal to lambda, so 28. So if I have 7,000 lines of code, on average there should be about 28 errors. And same thing for the standard deviation. So again, we have lambda equals 28, since they didn't change my lines of code. So variance of x equals lambda, or 28. So my standard deviation is the square root of lambda, square root of 28, 5.29. Okay. So again, we're going to skip Poisson. Okay. The rest of this section was just, I put a bunch of problems